Hello, welcome back. In this short video, I have added two problems in which you can determine the distribution of uh, functions of a continuous random variable. In the first example, you can see that y is equal to x square is the function of x. And what I'm doing in this problem is I'm finding directly the CDF of y after quoting the range of the function 3x square. Here you see that the range of the transformed variable y is equal to x square is set 3x square 0 less than or equal to x less than or equal to 1, which is equal to 0 to 1, because when x is equal to 0, 3x square is 0, and when x equal to 1, 3x square is 1, and as x varies from 0 to 1, this 3x square changes from 0 to 1. So this is the range of the new variable. Okay, and here I'm determining the distribution function of y directly. That is, if y of y is equal to probability that y less than or equal to y, and I am writing this y as x square. So this is probability that x square less than or equal to y. That is probability that x less than or equal to root y, which is equal to 0 to minus root y integral. Here I am evaluating the probability of x less than or equal to root y as 0 to integral 0 to root y fx dx. Okay, and that is equal to 0 to root y integral 3t square dt. That is because 3x square is the distribution, PDF of x. So I change the variable to t. That doesn't matter, because after substituting after integration, you will get the term in terms of y. So it doesn't matter whether you are using x or t or s, whatever variable. So this on integration, you see that this is equal to y to the power of 3 by 2. Y varies from 0 to 1. Okay, so you can consolidate the distribution function as 0 for y less than 0, and 1 for y greater than 1, and y to the power of 3 by 2, 0 less than or equal to y less than or equal to 1. Okay, and you can differentiate this distribution function, because density function is obtained by differentiating the CDF for continuous random variable. So the density function is this: fy of y is equal to 3 by 2, y to the power of 1 by 2, y varying from 0 to 1 and 0 elsewhere. Okay, so in this problem I am writing the distribution function directly by integrating. Earlier I was using the formula for fy of y. Here, instead of it, I am directly determining this CDF. That is the only change. And again, another problem, I am using another problem. In this problem also, I am finding the distribution function CDF or DF directly. Okay, and you can see that in this function y is equal to 1 minus x to the power of 3. If you take this as g of x, you can have the range of y as 1 minus x to the power of 3, x lying between 0 and 1, and here also the range is 0 to 1, because when x takes a value 0, y takes a value 1, and when x takes a value 1, y takes a value 0. Therefore, after all, the range is 0 to 1. And a distribution function can be written like this: probability that y less than or equal to y, and you know y is 1 minus x to the power of 3, so probability that 1 minus x to the power of 3 less than or equal to y, and you can take this is 1 minus x is less than or equal to y to the power of 1 by 3, and you can have minus x less than or equal to, and in order to change the sign of on both sides, you reverse the inequality, and you take the probability as probability 1 minus probability of the complement, and you can see that this is 1 minus 0 to 1 minus y to the power of 1 by 3 ft dt, and on direct integration you will see that it is equal to this. Okay, so distribution function is written as fy of y equal to y between 0 and 1 and equal to 0 elsewhere. Okay, and this is of course a continuous distribution function, and you can differentiate this CDF to obtain the density function. Okay, so the density function is f of y is equal to 1 for y less than equal to 1 and y greater than 0 equal to 0 elsewhere, which is nothing but the distribution called uniform distribution. Okay, I have added only these two problems only for the sake of grasping how the distribution function can be directly determined. In the same way, you can proceed with the earlier problems also, no problem. Okay, and you try with that steps also. Okay, thank you.